Okay, good morning everybody. Welcome back to non-Euclidean geometry.
Good morning.
Good morning. The plan for today is we're starting something new. We're going to talk about I'm supposed to say Euclid before axiom. We're going to talk about Hilbert's continuity axioms. I've got my usual office hours next few days, 11 each day, and 2 to 3 today and Wednesday, and 1 to 2 tomorrow. I haven't got the new homework set yet, but you will have. I will do that in the next couple days, and there is going to be a quiz on Wednesday over the congruence axioms. Notice that for the quiz Wednesday it says "con," meaning congruence axioms, not the stuff we're doing today. I apologize for taking so long to get homework 3 passed back. Tried to be a little bit quicker on homework 4. Last week was kind of a hectic week. I've posted solutions on Canvas for homework 3. You're welcome to take a look at those. Compare what you have to my own. Anybody have any questions before we get started for today? Okay, in that case, here's the joke of the day. One day, a mathematician decides he's tired of doing math and doesn't want to be a mathematician anymore. That's the joke. That would never happen. I know. So it goes down to the local firehouse and says, here I have stuff for you. Pick them up on the roof. So it goes down to the local firehouse and says to the fire chief, Mr. Fire Chief, I would like to be a fireman. The fire chief says, you seem like a respectable person. So I'm going to give you a test. So he takes the mathematician to the alleyway back behind the firehouse and says to the mathematician, all right, I'm going to give you 3 things. Suppose you have a spigot, a hose, and a dumpster. And suppose the dumpster is on fire. What would you do in that scenario? Mathematician thinks about it for a minute and says, well, I would connect the hose to the spigot, turn the hose on, and use the water to put out the fire. Fire chief says, oh, very good. Now, what would you do if you came down this alleyway and you saw that the dumpster was not on fire? Mathematician has to think about that one for a couple minutes. Finally, he replies, well, the first thing I would do then is to light a match and set the dumpster on fire. Fire chief says, what? That's terrible. Why would you set the dumpster on fire? Mathematician replies, oh, that way I've reduced the problem to one I've already solved. Okay, so the plan for today is we're going to talk about our final set of axioms. Let me pass that back.
Yes, sir.
So, we've talked about incidence axioms. We've talked about the betweenness axioms. We've talked about Hilbert's congruence axioms. This packet, we're going to talk finally about one last kind of new set of axioms called the continuity axioms, collectively. And these are going to be axioms that are, unlike what the previous sets of axioms, are not always going to hold in the models that we're interested in. Sometimes you'll have all of these axioms hold, sometimes you won't. And in either case, if you have the instance betweenness and congruence axioms, that's still enough in general to give you a pretty interesting model of geometry to look like. And unlike the other axioms we've seen, these are a bit more spiffy, a bit more egotistical, in that they all have special names. They're not just going to be congruence it's not going to be continuity axioms 1, 2, and 3, like in the last few packets. So these are all going to be axioms that have names to them. And depending on which of these continuity axioms hold, you're going to get different types of labels for models of geometry, like Hilbert planes, Euclidean planes, etc., which we will talk about towards the end of this packet. But the first axiom we're going to look at is the circle-circle continuity axiom. Or that principle, excuse me. What the circle-circle continuity principle says, if a circle gamma has one point inside and one point outside another circle, gamma prime, then the two circles must intersect in 2 points. So, for picture to go along with this, let's say here's our circle gamma, and here is going to be our circle gamma prime. Luke, can we find a point on the circle gamma, meaning on the circle itself, that we would consider to be outside the circle gamma prime?
Yes.
Does this point work?
Yes.
Yeah, we can call this, I'm going to call this P0, PO, the outer point. A point that's on gamma but outside of gamma prime. Joel, can we find a point that's on the circle gamma that we would say lies inside of gamma prime?
Yes, it's be like where you're looking at the shape. Yeah,
Like this?
Yes.
Yeah, I'm going to call this PI for inner point. So what the circle-circle continuity principle says is that if this sort of scenario occurs where we have these two circles, gamma and gamma prime, where gamma has at least one point outside of gamma prime and at least one point inside of gamma prime, then gamma and gamma prime have to have two different intersection points. Yellow chart. Which turns out, in this case, it sort of looks like they do. Those are going to be our two intersection points. And so if the circle-circle continuity axiom applies, then there's no way for gamma to have points inside and outside gamma prime without the circles having to intersect at some points. Sort of like in Calc 1, if you think back to the intermediate value theorem. Intermediate value theorem from Calc 1 basically says if you have a continuous function and at one point your function is below the y-axis and at another point your function is above the y-axis, then the function has to be 0 at some point in between. Like, as long as it's continuous, there's no way to get from a point with a negative y value to a positive y value without actually crossing the x-axis at least one point in between those two values of x. As long as your function's continuous. And the same sort of thing's going on here. There's no way for gamma to have a point outside gamma prime and inside gamma prime without there being some point in the middle where the two circles actually intersect each other. Any questions or comments about the circle-circle continuity principle? Jared.
So we can use this to cover the whole in postulate 1. Or, proposition 1.
And for my next question, if we assume this to be true, what hole in a previous proof that we've seen does this actually fix? Jared, what's that? Proposition 1, you say?
In proposition 1 for the equilateral triangle, when we drew the circles and assumed they intersect.
Yeah, that's exactly it. So if you recall, Euclid's Proposition 1, which we looked at way back towards the end of the first packet of the semester, we said that Euclid's Proposition 1, Book 1, Proposition 1, is the one that said on any line segment you can construct an equilateral triangle. And the idea was you start by making a circle centered at A that passes through B. Swoosh. You make a circle centered at B that passes through A. Swoosh. And what Euclid said in there was take a point at which these two circles intersect, call it C. Construct segments from C to A, C to B, and then CA equals AB equals CD. Poof, we have a equilateral triangle. But the issue, if you recall, that we had with this proof is how did we know that there had to be a point at which the two circles intersected each other? If we assume circle-circle continuity principle, we can fix that. The issue was we didn't have any reason to know that our two circles intersected. But if we assume the circle-circle continuity principle, the CCCP, not to be confused with the Chinese Communist Party, then the point C where the circles intersect must exist. Dr. Gerstle, what circle-circle continuity principle tells us that 2 points have to exist? Yeah, but that's not really important for the proof. We just need at least 1 point to exist where the two circles intersect in order to be able to construct the equilateral triangle and make this work out. Although you could say from circle-circle continuity principle, you could construct not one, but 2 equilateral triangles on AB using the same basic argument. Just do one with C up here, do another with your other point, C prime down here. Yeah, good observation, Jared. And in fact, we think that Hilbert actually had this as an axiom specifically with proposition 1 of Euclid's elements in mind. Because this is kind of the first sort of logical whole in the elements. Sad to say it's not the only one, but be nice to Euclid, he did his best. Circle-circle continuity, we think Hilbert said, like, I want to specifically assume this point would have to exist in order to be able to kind of fix this hole in Euclid's elements. Because if you recall, Hilbert was coming up with all of his axioms in order to come up with a system that's logically more consistent, that you can prove more things, that you can kind of fix some of the logical gaps within the elements. Hilbert very much had the elements in mind coming up with his axiomatic system. Any questions about circle-circle continuity? I have a question. What if our circle gamma looks like this? And what if our circle gamma prime looks like this? How many different points? How many points are there where these two circles intersect? Assume Dr. Gerstle is capable of perfectly drawing what's in his head. Right? There's only 1 point of intersection. Is that right? Circle-circle continuity principle? Maybe.
No, because wouldn't that mean there's not a point inside gamma prime circle?
Yeah, gamma certainly has lots of points. In fact, almost all of them outside of gamma prime. But gamma in this case does not have any points inside of gamma prime. It has a point on gamma prime, but none inside of gamma prime. And so I would say in this scenario, circle-circle continuity principle does not apply. And that since there's no point inside of gamma prime, there doesn't have to be it's okay if the circles just intersected at 1 point, or potentially not at all. In order to guarantee 2 points of intersection, you need to have, or, if I'm really feeling cheeky, in order for it to guarantee that there exists two different points of intersection, you have to have at least one point inside of gamma prime and at least one point outside of gamma prime. So here, you only have points outside and one point of intersection. Here, there's no points inside. Here, there's no points outside. And so circle-circle continuity wouldn't apply in any of these scenarios.
And does this one work the other way? Where if you have a circle that intersects at 2 points, then you get the first part?
What do you think?
Well, yes, in all the models I'm thinking of.
Well, if we try and draw a picture, if you have circles that intersect at 2 points, it certainly would appear that there's at least one point outside and at least one point inside. What if your circles behave like this, though? Have you considered if this is gamma, and that's gamma prime?
Oh, okay.
It depends on how you define circle. And I would say you can't directly say from this that the circle-circle continuity principle of that its converse is true, that if the two circles intersect at 2 points, then there has to exist a point outside and a point inside. I will say, however, that in Euclidean geometry, the converse would be true. It just doesn't immediately logically follow from the circle-circle continuity principle itself. You'd have to use that and a bunch of other stuff about properties of how circles behave and how something, yes, like this, is a Pac-Man and not a circle. Seth, do you have what else? Thanks. Any other questions or comments about circle-circle continuity? So, let's look at the big boy axiom. Turn the page. This axiom is going to imply all the other continuity axioms, including circle-circle continuity, which is going to be Dedekin's axiom. And since you all have the packet in front of you, I'd prefer not to have to write all of this down. But suppose a set of all points on a line L is the disjoint union sigma 1 union sigma 2 of two non-empty subsets such that no point of either subset is between 2 points of the other. Then there exists a unique point O on L such that one of the subsets is equal to an array of L with vertex O, and the other subset is equal to the complement. Everyone all right with that one? Yeah?
No.
No? You like to see a picture?
Yes, please.
Yeah. So there's a lot of terms in this one that are getting thrown about, so I think I'm going to go through and talk about what does this one mean in great detail. Especially because this is a powerful axiom, and that if this axiom is true, all the other continuity axioms in this packet are going to have to hold true, including circle-circle continuity. So what this is saying is, if this is true, take some line in your model. And the line I want to look at in the model is L is going to be the set of points x comma y that are going to satisfy, let's say, I don't know, x minus y plus 1 equals 0. Which is the same as saying y is equal to x plus 1. This is going to be our line L. And what we're going to do is we are going to take this line and we're going to split it up into two separate sets. Into two sets that have two properties to them. That they are disjoint. And disjoint is a mathematical term that just means the two sets don't have any elements in common. They do not overlap at all. We could actually say they have an intersection is empty. They don't have any points that are in both sets. And we also want to split up, we also want our sigma 1 and sigma 2, our way of taking this line and splitting it up into two sets, to also satisfy that our two sets, I should say sigma 1 and sigma 2 are disjoint. And also, no point in sigma 1 is between any 2 points in sigma 2 and vice versa. So if this is a point, for instance, on sigma 2, and this is a point on sigma 2, then all the points in between there also have to be inside of sigma 2. Can anybody come up with a way of defining two sets sigma? Oh, and I guess just in case it's not clear, we want sigma 1 union sigma 2 to give us the whole line. So in other words, if we take all the points in sigma 1 and combine it with all the points in sigma 2, we get every single point on our line L. Your challenge, and go ahead and take a minute or two to do this, is come up with set sigma 1 and sigma 2 that'll make this happen. Split the line up into two sets where no point in one is between any 2 points in the other. The two sets have no points in common, and if you combine the two sets, you get the entire line. As always, you're welcome to talk to your neighbors and or ask me any questions you might have. And if you think you have a way to do it, share it with your neighbor anyway. That's something you will need to decide. Because you do want every single point on your line, including, say, whatever your O is, to say.
No, it's given a single.
Or to be in one of your things.
Yeah, so we're good. Yes.
Shut out your mouth. That's not food. Is that an iron bar? You're eating an iron bar, that'd be a different story. But that's not an iron bar. Doing all right over here? You got an answer?
Yeah,
I look forward to hearing it.
Yeah, I like it. I think we need to exclude it.
If you have one way of doing it, see if you can come up with another way.
Go with 100. Right. Yeah.
Wait, your hands on your own work. Quit trying to steal Megan's thoughts. It's rather rude. I know, that was rather obvious.
And then
Especially when you wonder the first time.
Oh, not entirely
So on
wrong.
the scale of 100.
I'm just kidding. We talked about
It's a
these.
little bit above that.
Sigma 2 is,
We talked about like how much I forget you're not a senior this year.
You're gonna just, I'm just gonna show up next year, everyone obnoxious is gone, and then
But then Megan else.
and then you're gonna be looking at your
so
class roster,
that's
like,
for the origin, Sigma 2 wouldn't exist at,
oh, I will, oh.
and then.
All right, let's come back together here and talk a little bit about what you all found. Sydney, sounds like your group had a way of defining rays sigma 1 and sigma 2 that'll get the job done. Would you like to share what you came up with?
We just said select any point, so we do, x is 100 by 101, so select one point, and then set sigma 1 equal to or greater than that point, and then sigma 2 less than, and you can define that on the x or the y-axis.
Okay, give me your point of choice.
100, 101.
Okay, so if we take, let's say, O is going to be the point 100, 101. How would you define sigma 1?
The ray following that point, like define a point B that's greater than I, and then the ray of that.
What does it mean for a point to be greater than 100, 101?
Okay, then define a point B, like 101, 102, and make the ray.
Okay, we define one point, and now our point has become a ray. How about this? Set of all points x, y such that y is equal to x plus 1, and let's say x is greater than or equal to 100. Does that work? So in other words, if we go out to the point 100, 101 on our graph, and look at all the points on this line whose x-coordinate is at least 100, that's going to be your sigma 1. Okay, what would your sigma 2 then be?
It's going to be same, but x is strictly less than.
Xy such that y is equal to x plus 1, x is strictly less. So in other words, I don't have any I need more colors. That's going to be your sigma 2. Pretend these are overlapping perfectly because I don't have enough colors to match them up to make it the way I want it to be. Well, let's take a look. Do these two sets have any points in common? Do these two sets, if you combine them, give you the entire line, meaning every point on the line in one of these sets? Is it the case that if you were to take any 2 points in sigma 1, everything in between them is also on sigma 1? And ditto for sigma 2. I like it. Anybody have a different way of doing this? That was different, let me say, other than just choosing x to be 100 instead of something else. Joe?
I just made like the arrow that's like in the positive quadrant one. I said that was sigma 2, and then so then sigma 1 would be the opposite sign of sigma 2.
Okay, so basically you said that the point in the middle you just let be on sigma 2, and so your sigma 2 went up this way, but sigma 1 went that way?
Yeah.
Okay. That would be a different way of doing it. That's really pretty much the same. You're just kind of swapping the names of your two sets. Which one is sigma 1, which one is sigma 2.
Okay, I did 3 points on L, A, B, and C, with A between C and B.
Okay.
Okay, and then I said that ray AC was sigma 1. 2 with all the points on ray AB except point A.
Like that?
Yeah.
So in other words, you did the exact same thing.
Yeah.
Just define you picked more, you had more points in mind.
Megan really didn't like that I did it that way.
Megan, why didn't you like that you did it that way?
I feel like based on a definition of array, you have to have a concrete starting point, and the fact that it's just
Epsilon.
it's an epsilon neighborhood. Like you can't get there's no A.
I did.
And
So
epsilon neighborhood, you're gonna have to explain that one to me.
you're just getting infinitely closer to A, so there's not a starting point.
So in other words, sigma 2 is going to be array like minus its starting point, and the other one is just going to be array including its starting point.
It just doesn't really feel like a ray.
It's a compliment, relative compliment.
I would say that in this drawing, I would agree. Because technically a ray always has to have a vertex, a point at which it starts. And sigma 2 in this case, you're right, doesn't have a starting point to it. Something epsilon neighborhood, yes, you could do it, but you could say something about epsilons, I don't want to. The moral of the story, though, is that every way that you can split your line up into two sets that have these properties, one of them is going to have to be a ray. And then the rest of it, the other set, is going to be the complement. And by complement, I just mean everything else. So what Dedekin's axiom is saying is that you can always do it, any way of doing it, one sigma is a ray. The other sigma is the complement of that ray. I.e. everything else on the line. In general, when you take the complement of the set, you're thinking everything that's not in my set. And so in this case, the complement of that ray, in this case, sigma 1, Elaine and Sydney, for the way you had it. Joel, how you described it to me, I would say sigma 2 would be your ray. And then everything else is just, and then the other sigma is just going to be what's left over. Whatever else is necessary to make up your line. Which in sort of this Euclidean model would basically be another ray minus the vertex of that ray. And if Dedekin's axiom holds true, then the only way you can take a line and split it up into two sets having all these properties is if one of those two sets is in fact a ray. In Euclidean space, that's what's going to happen. Something funny, Elaine?
I'm just happy that Megan and I are fighting.
Do I need to separate you two?
No.
Good. Any questions or comments about Dedekin's axiom? Dedekin, by the way, you mathematicians did a lot of analysis / geometry type stuff. We're going to see his name pop up again later, and I'll talk more about him at that time. So, turns out, if you know that Dedekin's axiom is true, it's going to imply a whole heap of continuity axioms, including the circle-circle continuity principle from earlier. So, just kind of write out what are some consequences of Dedekin's axiom. Too lazy to write up Dedekin, apparently. So one is, if Dedekin's axiom holds true in the model of geometry that you're looking at, you're automatically going to get circle-circle continuity, meaning what we talked about earlier has to be true. we're going to get the line circle continuity principle. Line circle continuity principle, which basically says if you have a line that passes through a point inside of the circle, then the line has to intersect the circle at 2 points. So in other words, we get a circle, let's say, pick any point, I don't know, let's say this point. If we know that there is some line that passes through this point P inside of our circle, then that line has to intersect this circle in exactly 2 points. So let's say we know that we have a line L that goes through the point P. The only way for that to happen is if our line ends up crossing through our circle at these 2 points. Question?
Why does this follow from?
Not obviously. There's a lot of math that goes into why does this happen as a result of Dedekin's axiom. Basically, Dedekin's axiom talks about weight. Basically, the idea, as kind of a general thing, I think is, suppose you have a point P on the line and outside of it, you basically have to split the line up into 2 sets. The set of points on one side of P and the set of points on the other side of P. And Dedekin's axiom implies that one of those sets has to be a ray. And then you can say something about how rays and circles intersect each other. And you're also not just going to be relying on Dedekin's axiom to make this argument. You're also going to be relying on incidence betweenness congruence axioms. They're all kind of necessary in order for this to work out. Specifically betweenness axioms because we need some definition of what between means in your space in order for this to make any sort of sense. Yeah, good question. How do these follow from Dedekin's axiom? There's a lot of kind of underlying math and gory detail that I don't really want to get into that kind of makes that happen. But it does. So we also got another one which is basically the same thing but for line segments. We could talk about segment circle continuity. Principle, which says if you have a circle and if you have a line segment AB where one point A is outside your circle and another point B is inside your circle, then the segment AB has to intersect your circle once. There's no way to have a line segment start inside your circle and end outside your circle without the segment actually intersecting your circle at one point. Okay? You can't teleport. You can't have a segment teleport from being inside to outside the circle. It's got to cross it to go from inside to outside or vice versa. And if you notice, all of these are really saying the same thing. Circle, circle continuity, line circle continuity, segment circle continuity. The idea that if you have sort of a line that's both inside and outside a circle, it has to cross the circle in order to make that happen. Of course, for line circle continuity, you need to have this point inside your circle in order for it to be required to give you these 2 points of intersection. Because otherwise you could have something like this where the line just doesn't intersect the circle at all. Or you could have something where they intersect once if you have a scenario like this occurring where there's a point on your circle that the line hits but nothing inside of the circle. What line circle continuity tells us, though, is if your line happens to pass through a point strictly inside, not on, but inside your circle, then you have to get these 2 points of intersection. Any questions or comments on any of these? The idea here of continuity all comes down to the fact that that all of these principles are essentially saying lines and circles are continuous things in the sense that your line can't have a gap in it. You can't say that, all right, I'm going to have a line go from outside to inside by doing something like, and then my line is non-continuous and has a jump in it to do something like this. The idea of these being continuity principles is that if we have these continuity principles occurring, we're assuming lines and circles are continuous things where your line can't jump from being outside to inside of, say, a circle without having this point of intersection between the two. Hey.
Does it matter how we define inside? I was not sure if we need to have the or if we do. I just don't know
Ooh,
about it.
good question. How do we define inside? It's easy to say something like, if this is a circle, that point's inside while that point's outside. But a little bit harder to give like a precise definition. In Euclidean space, you could say something like, well, this circle is a set of points whose distance from O is exactly equal to R. And you could say, then inside is a set of points whose distance is strictly less than R. The outside is a set of points whose distance is strictly greater than R. And typically, in order to do that, you're going to need to rely on some of your notions of congruence. What does it mean for a distance, if you're comparing two distances, for one to be less than or greater than the other? In non-Euclidean models of geometry, especially in models where you're not defining congruence as being the distance between the two is the same, and so your definitions of circles might not rely on distance per se, then it's a lot trickier, and then you have to be a lot more careful in how you would define inside versus outside of, say, a circle. By the time we get to the continuity axioms, we have so many axioms at this point that any model that would satisfy one of these, along with incidence between these congruence axioms, is going to be something that at this point looks a heck of a lot like R2. And if it looks, and so much so that you probably have some notion of distance that's being used that you could use to define inside and outside of the circle that way. Does that answer your question, Dean?
Yes.
It's a good question to ask though, because that is something we never carefully defined. I would call inside and outside of circle model undefined terms that are model dependent, sort of like what we've been using for incidence and between and congruent for the last few weeks. We're also relying on something called Jordan's curve theorem, which basically says if you have any sort of contour in your space that kind of, like any sort of loop, like you could think of it as being like a path that starts and ends at the same point like this, it's always going to divide up R2 into a bounded space, which we'll call the inside, and an unbounded space, which we'll call the outside of that curve. We're not going to get into that much in this class. We'll learn more about the Jordan curve theorem, take topology, or complex analysis. But there's some stuff at work that tells us like a circle is always going to divide up a space in Euclidean space. It's going to divide up the whole space into a bounded inside, bounded in the sense that it doesn't go off forever in any direction, and an unbounded outside. Any other questions or comments about any of the continuity axioms thus far? Oh, let's see, 5 minutes. We have time for Archimedes. Yeah, we have time for Archimedes. All right, so one last consequence of Dedekind's axiom is going to be an axiom called Archimedes' axiom, likely recognized from, I don't know, discovering formulas for things like volume, jumping out of the bathtub and shouting Eureka, where if CD is any segment, A is any point, R is any ray with vertex A, then for every point B not equal to A on R, there is number n such that when CD is laid off n times on R, starting at A, a point E is reached such that n times CD is congruent to AE, and either B equals E or B is between A and E. Like Euclids axiom, this one needs a picture to make any sort of sense. So here's the scoop. We're going to suppose we have some segment CD. And this segment is going to be our measuring stick. So whatever this is, we're going to say that this segment has a length of 1. What does that mean? We are defining a length which we will call 1 to be equal to the length of this segment. And now we're going to suppose we have some ray starting at some point A. And we have some point B on this ray. The idea behind Archimedes' axiom is if we start at the point A and we basically start laying off copies of CD, these copies of the segment of length 1 on our ray. So let's say if this is length 1, let's say here we get to a point A1, here we get to a point A2, here we get to a point A3, where all of these segments are going to have the same length as our measuring stick, length 1. And then let's say here's going to be our point E down here, which will be our A4. Make sure I'm reading this right. There's number n, such that when CD is laid off n times on R starting at A, point E is reached. And here, the point A4, which we're going to call E, is a point that's reached laying off our measuring stick, CD, on the ray AB, n equals 4 times. So we had to use 4 different copies of our measuring stick to get this point out here, E, where now we've reached a point E where B is between A and B. So in other words, what this says is no matter how far out you pick a point B on your ray, given any segment to start with as your measuring stick, you can keep laying out that segment enough times, make enough copies of that segment on your ray, so that eventually you'll get to a point where your point B, no matter how far from A you chose, will be that number of copies of this number of copies of your measuring stick away from the starting point. So in this case, we could say B is approximate. We could say that AB is approximately, I don't know, 3.4. That the length of the segment AB is approximately 3.4 if the length of CD is 1. In the sense that the length of the segment from A to B is about 3.4 times the length of the segment from C to D. If we laid off segment CD enough times, wrong point. So here's one copy of CD. Here's another copy of CD. I am totally butchering this. There's a copy of CD. There's a copy of CD. Here's a copy of CD. And here's our last copy of CD. By laying off CD enough times, we eventually make it so that that number of copies of CD has length greater than A. And we end up where A is C is between A and B. The B equals E possibility that's mentioned at the end of Archimedes' axiom comes from the fact that if B is, say, exactly 4 copies of CD out, then we could have that E and B give us the same point. All right, that's going to do it for today. When we come back on Wednesday, we are going to have a quiz and then talk a little bit more about the relationship between the different continuity principles. Hope you all have a good rest of your day. See y'all on Wednesday.